we are going to do a hypothesis test for a mean. So a recent survey of 41 BMCC statistics students, we asked, how many hours of TV do you watch per day? And I've been collecting this data for a while, and you're going to work on this 41. I'm going to work on a slightly different set of students. We're going to complete a full hypothesis test procedure. And so there's a model for this in the week 7 information of the course. Make sure you go through all the steps. That's what I'm going to do here. Continue reading. We want to determine if BMCC statistics students watch less television than Americans in general. And we're going to use the fact that on average Americans watch 5 hours of television per day. So that includes things like broadcast TV, streaming, YouTube, you name it. Anytime someone's actively watching some kind of video thing on a screen. The standard deviation of 1 hour per day we don't need here. We'll look at that in a couple of weeks. So anytime I have a hypothesis test or a confidence interval, the first thing I want to do is identify the population and the population parameter. Population in this case is BMCC students, or maybe BMCC statistics students. The population parameter is an average. I'm using mu down here to indicate it's a population mean, and it's the average amount of hours per day that BMCC students watch TV. The null hypothesis comes from the study I read about Americans watch 5 hours of television per day. And the alternative hypothesis is this claim in the first sentence is that BMCC students or stat students watch less than that. So null hypothesis mu is 5, alternative is mu is less than 5. So I want to start drawing a sketch of this, and then we'll add to the sketch as we move along. So we draw our best bell curve, and then we write down that this is a mean, so mu, and the value of the mean from the null hypothesis. Then we make a note of if it's a left tail, right tail, or two tail, and mark our significance level. So alpha is the significance level. How important is this? So this is important, but not too important. If students watch too much TV, it's going to get in the way of studies. If they watch too little, then maybe they're missing out on some important news from the world, or just recreation, which is important too. So to get the critical value here, I have to go to stat key. So I'm going to do that next. So I'm going to go grab the data and take a look at stat key. So I'm going to use a data set of 42 students that's different than the 41 you're playing with. And I'm going to highlight it, copy it, and come over to stat key. And I'm doing a hypothesis test, so I'm in the third column, and I'm working with means, not proportions, and I have a single mean I'm working with, the mean hours per day of students. Two things you want to do here before you get started: make sure you have the right data set. If the data set isn't given that you want, then you will have to edit the data set by highlighting, deleting, and pasting in, I copied it, your data. Double check, do you have a header row at the top? If you don't, uncheck this. If you do, make sure that's checked. And I don't have an extra first column identifying what each of these numbers belongs to. All right, next thing we need to check is, do we have the right null hypothesis? I did not, so I'm going to set it to 5. And then over here I can see a dot plot, which is a kind of histogram of this data. And it looks to me like a few of these numbers are outliers. Most students seem to watch around 3 hours per day or less, and there's a few that watch significantly more than that. So if we were to plug this into a box plot generator, we'd probably see that 2 or 3 of these numbers on the right are outliers, according to the IQR rule. So once we have the data in there and we set the null hypothesis, we're ready to generate a sampling distribution. Now, remember what a sampling distribution is. This is a tricky concept. Each of these points here represents the average of some other sample. And so if you look over to the right here, every time I point to one of these dots, bottom right shows me what that sample looked like. And notice that each time it's slightly different than the sample I started with. So what StatKey is doing is, based on this original sample, it's trying to make up other groups of 42 individuals. And it's also assuming that the average should be 5, but there's always going to be deviation from that. And so it's trying to rebuild a bunch of samples of 42 people using some randomization based on 5 as the average. So notice 5 is ours is in the center here. So I have 1,000 means here. Each mean is from a sample of 42 individuals. Okay, so 1,000 isn't enough. We want to build more than that, and I recommend you go over 5,000. I'm going to go up to 7,000. So as you generate more and more samples, and again, now I have 7,000 samples of 42. So just let's keep a couple things straight. Although we're simulating what a population distribution might look like, each of these is not an individual person, it's the average hours of TV per day for 42 people. So I have 7,000 samples of size 42. This is not the population there, this is not the population here. This is a sample. There's another sample here. There's 7,000 other samples here. I happen to look at 7,000 samples of size 42. The population, well, that's either BMCC students or BMCC statistics students, and that's not exactly represented here. This is just kind of a simulation of samples of size 42. Crazy concept, takes some getting used to. This is again what's called a sampling distribution, which is a distribution, histogram, of sample means in this case. Other thing I'm going to do here is identify I'm doing a left tail, and I'm going to enter my 5% as a decimal, and this tells me that the critical number is 4.387. And every time you run a simulation like this, numbers like this will be slightly different, but they should be in the ballpark of each other. So if I look earlier when I ran this, I had 4.385. This time I get 4.387. They're about in the same place here. So what that shows is that 5% of these 7,000 samples had an average TV time of 4.387 hours. If I find a group of 42 people who have an average less than that, I would consider that to be unusual. If I have a group of 42 students who watch on average more than that, then that falls in line with the national average. So next we need to look at what our sample says. So I want to, again, this is my significance level, this is my sample or test statistic. Next step in the procedure is to plug in your sample data. So I just replace the number on the horizontal axis here with the sample mean of 3.35, and that's way off the chart. This is showing me here that of the 7,000 simulated samples that StatKey looked at, none of them had an average of 42 people watching 3.35 hours per day or less. Okay? And again, that's not an individual's measurement. We're looking for groups of 42 people that have that average or lower. So once I plug in the data in my sampling distribution, this number up here is what we call the p-value. So it's the probability of finding another group of 42 students who watch on average less than 3.35 hours, given that we were expecting them to watch about 5 hours compared to the rest of adults. So I need to make a note of that in my graph. New page. All right, so here again is my significance level and critical value, and this over here is called the critical region. So if my sample data falls in the critical region, that's one piece of evidence that says you should reject the null. So next page. So I mark, based on these numbers, scaling the number line, where does my 3.35 live? It definitely lives in the red zone, which is evidence number one, because my sample statistic is in the critical region, that I'm going to reject the null. Evidence number two is finding the p-value. The p-value is the area under this curve here, in this case to the left, because I'm doing a left tail test. And 0 is definitely less than 5%. My p-value is less than alpha. So that's the second piece of evidence that says reject the null hypothesis here. Keep in mind that some of the questions you're asked don't ask about the sample statistic in the critical region. They just ask what's the p-value. I always find both because I want to double check. These two pieces of evidence should always agree. They should always agree to reject the null, or they should always agree to fail to reject. If they disagree, that means you screwed something up somewhere and you should start over. So both pieces of evidence point to rejecting the null hypothesis. So next thing to do is write up some interpretations of what all this stuff means. So what does my p-value of 0 mean? So that this p-value is the probability of finding another sample of 42 people who have a mean number of hours of TV per day that's less than the 3.35 hours that is in my sample. Now this is on the expectation that they should have been watching about 5 hours per day. Okay, so according to the national average, if I get a good random sample of 42 people, their average amount of TV watching per day should be about 5 hours. Here I found it's way less. Okay, so because this probability is so small, something is wrong with my assumption that BMCC students watch 5 hours. It can't possibly be right because I did find 42 people, and the computer says the probability of finding those 42 people is 0. So again, that means there's a flaw in my assumption. My assumption was they watch 5 hours per day, right? Because 5 hours was in the middle of my distribution here. Okay, so that was a faulty assumption. That says reject the assumption that it is 5 hours for BMCC evidence, or some BMCC students. So that brings me to my conclusion. The conclusion is like what I would give for a press release. So we have sufficient evidence that BMCC students watch less TV per day than the national average of 5 hours per day. Now, can I say that BMCC students watch 3.35 hours per day? The answer is no. I would have to do a confidence interval to set a range and a margin of error on that, which I didn't do here. And often we do confidence intervals and hypothesis tests hand in hand because we're trying to estimate some parameter or test something about that parameter. And again, a parameter is some measurable attribute of a population. In this case, how much TV per day BMCC students watch. All right, so that is the full hypothesis test procedure. The step-by-step process is located in the model for hypothesis tests in this week's material. So good luck with this. Contact me if you have any questions. Have a good day.